Hey there. Let's talk about functions in x86-64 YASM assembly. I'm just going to give you the basics of how to write a function. So let's get started here. First thing I want to show you is just a makefile. This is not a makefile video, so you don't have to worry about it too much. I just have it up because I need it for this demo. If you're interested in makefiles, that would be a really good thing. I'll probably make videos in the future about them, but for now we'll just say you hopefully have a script or a method already set up that allows you to compile or assemble assembly programs. So I'm just going to skim through it real fast. If you're interested, you can kind of study it. But basically, I have like a little define here that allows me to print out a message that looks nice. And then I define the repo path as the current path, and I take the absolute path of that. This is where the real work happens. I have YASM flags because I'm using the YASM assembler. I'm going to be assembling to x86-64. I like to convert all of my warnings to errors to make sure that I don't write sloppy code. Export debug symbols and export debug symbols for the linking stage too. The name of my executable is going to be called main, and then I just have like a little makefile menu here that I have set up. And well, I can just do make run or make debug as a little shortcut to run it in GDB. If you don't know GDB, don't worry, that's going to happen in a future video. And make clean, which just cleans the build area. I like a clean build area. And then this is the main command here. We're going to be using LD to do our linking because this is going to be a pure assembly program instead of a hybrid program, which would require GCC or something else. And then here's my program. Main ASM is going to get compiled down to main.o. And that's it for the makefile. Okay, so for the main assembly program, I have some stuff written up already here, but I think I'm going to modify it for this video. For starters, we have our data section, which hopefully you understand already. I'm just going to define a bunch of stuff in the data section, like I'm going to define the system call code to write a string, so I can print a message pretty easily, the system call code to actually exit the program. Remember, when you're writing a pure assembly program that has start as an entry point, you need to be, you're responsible for exiting the program. So the system call code is 60 there. And then I'm going to say exiting for success is a 0. That's kind of a standard thing. And then I'm going to make 2 file descriptors. For the standard input, it's going to be 0, and the standard output, it's going to be 1. Actually, I don't think we need that for this video. We just need standard output, but not standard input. And then I'm just going to make 2 strings. That's not my name, but I like those names. And then the BSS section, actually I'm going to get rid of that because we don't really need that for this video. And then I have a text section, which is where all the code is. We're going to begin our entry point. If you are writing a pure assembly program and this is your entry point module, again, you will have to make a function called _start. It's not actually technically going to be a function because it won't return anywhere. It'll actually just call the system exit service. And then I mark start as global so that the operating system can go into it, can call it from the outside. And then all I'm doing right now is just I'm printing a hello. So far this is not really a demo of functions. This is just like a very basic pure assembly program. All it's going to do is it's going to enter, it's going to print the hello message, and then down here it's going to do a system call to exit the program with 0 for success. So let's just see what that looks like real fast. I'm going to do make run. And then make run, you can see the first line, it just kind of prints. And then the second line, that's make, sort of echoing the command that I'm issuing. It's just going to assemble the main.asm into a main.o. And then it's letting me know that if there are any warnings, it will refuse to compile. And then I use the LD linker to link the main executable, and then I actually run the executable. So only below this line that I have highlighted right now is going to be the actual program. So you can see all it really did was just, print the message and then exit. Just, a little note here. I've probably said this in other videos, but the return code 0 is kind of a standard to indicate success for programs, which is very useful if you want programs to automate other programs. If I change the system, let's see, what is it? Exit success. If I just change that variable to a 3 so that I will exit with a return code of 3 instead of 0, then the operating system, or actually Bash, since we're in a terminal emulator, should consider the program to have exited in error. So you can see now it's like, hey, the Makefile system, oh not bash, the Makefile system is like, that program exited with code 3, something went wrong. And normally if you don't add any extra stuff into your Makefile, it'll just refuse to continue at that point. So I'm just going to change it back to a 0 and make sure that it still works, and then we'll get on to actually writing functions. So I'm going to go clear and make run, so it's a little bit faster for me to run this repeatedly. You could see actually the first time that I did that, the Makefile recompiled. Notice how it recompiled and relinked because I changed that source code. This is not a Makefile video, but I just want you to be aware one of the great reasons to use Make or a build system in general is because it makes it really easy to compile your code faster. Notice how if I didn't actually change, let's see, so I recompiled it because I just changed it again, but now I haven't changed it since I'm going to recompile or rerun. Make just kind of like skips reassembling that file because it hasn't changed. So it can make your compilations and assemblies much, much faster. So anyway, functions. Functions in assembly are kind of simple, and you'll realize that some of the stuff that we take for granted in higher level languages is being done for us automatically by the compiler. But in assembly, we have labels. So for example, this start entry point, that's actually a label, right? We just have like some valid symbols like characters, underscore, numbers. I don't think you can start a label with a number. Correct me if I'm wrong, but I don't think you can. So we have like a label, which is just like this collection of characters. And then we have a colon after it. And so you can jump into a label, which I'll talk about in a different video. But you can jump into a label, you can call a label as a function. And so a label isn't actually a function by itself. You have to treat it in a certain way in order to consider it a function in the abstract. So notice how there's no return statement at the bottom here. Let me write a function real fast. And maybe I will have it so that I have a function that just says hello for me. So I'll make a label down here, function that says hello. And I'll give it a label and I'll say maybe like say hello, and I'll do a little label there. First thing that you should do when you are trying to create a function is just put a return statement at the very end of it. That way it will return to the caller, because if you don't, then it's just going to continue to execute downward until it reaches no code, and then the program will probably crash. In fact, maybe I should do that. I'm going to do say hello as a label with no return. So it's not really a function now. It's more of just like a label that you can jump to, but there's no code under it. So it should, I'm not even sure this will assemble, but it'll definitely crash if we can call into this. So let me do, at the very start of our program, I'm going to type call say hello. Or actually, you know what? Maybe first I'll jump to hello. Jumping is going to be for a different video, but jumping just means go to that place. It's a go-to statement, essentially. You're not supposed to be able to return from a jump. If you jump somewhere and they want to jump back to you, okay, but it doesn't really follow the same design pattern logic as a function. So I'm going to immediately jump to the say hello logic and see what happens. I think that it'll crash. Here we go. Seg fault, core dumped. Oh no. So, hey, it crashed. So instead of jumping there, let's do a call. Now we're treating it a little bit more like a function. We still don't have the return statement down here, so it should still crash, I think. Let's try that again. Yep, it crashed again. Okay, because you're supposed to exit from the operator, or you're supposed to exit from the program properly to the operating system. So now I'm going to do a return statement here. There's never an argument for the return statement. You just simply return to the caller. This uses the stack. If you don't know what the stack is, I'll probably make another video about that in the future, but the stack, you know, it helps your program understand where it just called to and how to get back from it. It also stores local variables and things. But so if I have a call, it should jump down to the hello function and then return, meaning it'll just return to the caller immediately without actually doing anything. But the program should be able to continue without crashing. Notice how there's no crash here? All it does is print out the welcome message and then no problem. All right. So now I'm going to take all of this hello printing stuff and I'm just going to cut it and stick it inside of the say hello function. That way, when I call that function, it should still print hello. But now notice how we have less code to deal with in this primary function. One of the first things that programmers learn is that, we're human beings, we're not computers. It's really hard for us to write complex logic in a program without tools to help us and design patterns to help us stay on track, to help us, make sure that we're not going to be forgetting anything or screwing something up, or, to debug. So, one awesome design pattern is to write functions, because you realize in your program, you might be calling the same logic several times. So you're sort of like repeating a bunch of code. That already is bad. It's really hard to debug repeating code, and it's really hard to make updates to it, and it becomes unwieldy, right? So as soon as you realize you're repeating the same logic, the same code in several places, you should think about taking it and putting that logic into a function, and then just simply calling that function many times. It makes your coding a lot easier. And then once you put all the work into getting a function to work, you can just be done with it. As soon as you're sure that this function actually works, you can just put it to the side and just forget about it. You can stick it at the bottom of the source, or just ignore it, put it into a different module, whatever you want to do. And then the other parts of the program that you're still working on, they become a lot more simple. And so, because we're human beings, we need all the advantages we can get to write powerful code. So I don't have to think anymore about all the system call things that's happening to print the hello message. All I have to do is think about calling the say hello function. And of course, this is simple, but you can imagine using this for more complicated concepts in the future. So let's see if this still works, if I didn't screw this up. Notice how it printed the same exact message. And if I keep running it, the Makefile doesn't compile as much, but it still runs the program. If you don't believe me that this is inside of a function now, let's actually just call that same function many times. We'll call say hello. Let's say we call it 5 times. This should work. I'm going to run the program again. Notice how it printed that message 5 times. Just to reemphasize my earlier point, wouldn't it be a huge pain in the butt if you wrote out all the code for the system call and the message printing 5 duplicate times? Wouldn't that be hard to update? What if you had 100 of those in there? What if you had something that was really complicated and you called on it like 50 times? Wouldn't that be so much better than maintaining 50 different versions of the exact same idea of code, and making sure that if you needed to upgrade it or change it in some way, you actually got it right for all 50 copies? So this is way better. All right, so that's the basic idea for a function. Let's see, what else can I do? Let's make a function that just prints anything, because that would be kind of a good little practice in the arguments that we can use. Remember, in C++ and other languages, you have function signatures that you can use. So for example, say hello. We know for sure that say hello is not actually doing anything. It's not receiving any arguments, and it's also not returning anything. So if we know it's not returning anything, we can say that it's a void function if we're talking C++. We'll do the name here. We'll say hello. And in the argument list, we know that it doesn't take any arguments, so it's just say hello with nothing, right? Okay. So let's make another function that just prints something. And this function will kind of be a little redundant, because if you just sort of look at the system call here, we have to load up the system call with the standard output and the system write code. So that's going to be repeated. So we could move that into the print something function, but then giving an argument of like, here's the string I want to print, and here's the length of the string that I want to print, that is something that we can pass as arguments every time. So we'll be saving like a little bit of work, but it still, I hope, illustrates the idea. Okay, so maybe we will, print something. Okay, so print something, maybe we'll do the signature here. Print something will not return any value, so we'll just give it a void return type, and I'll do a description up here. Print a message given by a character pointer, a pointer to a string. I mean, technically, a pointer to one character is also a pointer to a C string, not a regular string class, but a C string. So I don't know how to describe it. I think I'll just say a pointer to a C string. And length, and integer length maybe. So that means the print something function should take 2 arguments. We want to be able to call that function and tell it, here's a pointer to the string I want you to print, and here's how long the string is. So Still talking about C++, I'm going to say character pointer P, and maybe I'll put like string just to remind myself when I look at this later. It's a pointer to the string, or like P char for the pointer to like the first character in the string, something like that. And then length. So the length is going to be a long because we're using 64-bit integers in this video. Long, and I'll just say maybe size or length or something. So now we can remind ourselves what's actually happening. I want to use the same symbol that I'm describing in this little prototype here, so I'm just going to copy paste it and use a colon. And then because it's a function, I immediately want to put a return statement at the very end. Okay. So then what I need to do is grab the incoming arguments. Okay, so, well, the first thing that every system call that prints a string should do, at least if it's going to print it to standard output, is it should start setting up the system call code registers, or the system call registers, to say, all right, the system call wants RAX to describe what the system call is going to do. We already have system write set up, so that just means we're telling syscall that we want to print something. Where do we want to print it? We want to print to the standard output, which if you look at earlier in the video, that was just a file descriptor of 1. So that's fine. Set up the system call. And then the next two things can be kind of variable. We can grab that from incoming arguments. So RSI wants a pointer to the string. We're not going to load hello string, but we're going to load whatever character pointer we were given in the incoming arguments. If you look at your assembly books, you'll know that RDI is the first incoming integer argument. We're not going to talk about mixed arguments with floats. If we just assume that we're only going to use integer arguments or pointer arguments, then the first one is going to be RDI. So that means by the time print something gets called, by the time we come into this code right here, RDI should be loaded with the pointer to the character, to the C string that we want to print. Again, this follows something called the ABI, which you should absolutely respect, even if you're the only one writing any of the code that you interact with. Your code will be bad and considered not good if you don't respect the ABI on this type of architecture. So we definitely still need to load RSI with the string pointer, but RDI is what's going to have the string pointer. So we actually already just ruined RDI when we were setting up the system call, didn't we? So that means we should probably either load it up backwards, or I think probably a better way to explain functions is, let's just use another register. So I'm going to use another register to sort of store our incoming arguments. I personally like to do this. I admit that this will cost you CPU cycles to sort of like move things around in registers, but it's still way faster than sticking something into a global variable, because then you'll be hitting memory. So first I'm going to say, let's move something into R12, and I want to store the incoming arguments. So I'm just going to write here, save the pchar, C string character pointer or something like that. So we're going to save it. And then the next thing we need to do is save the size, because as soon as we load up RSI, we're also going to be destroying the second integer argument, which should come to us in RSI. Okay, so I'm going to save that too, I guess, with R13. So I'm going to move something into R13, RSI, and then save the size of the string, C string. Okay, so we saved both of those. Now, when we load RSI, we can just sort of say, RDI is saved, and then when we load RSI, oh, that'll be when we hit RDX. Okay, I got confused. So we stored, R12 was the character pointer, and then for the length of the string, we stored that as R13. Also, for me personally, I feel like it's a pretty good idea to kind of make a comment at the very top, because this is assembly. It's really, really hard, right? Make a little comment at the top, just kind of reminding yourselves what you use all of the registers for. I know sometimes you'll use the same register for multiple purposes. You could either write that down, or you could consider breaking up your function into multiple functions. That's totally valid, and it probably will make your life a lot easier. Anyway, so I'm going to say register usage. And then I'm going to say R12 pointer to string, C string, and then I'm going to say R13 is going to be size of the string. And that seems simple, but remember, assembly, especially when you're new, it's really confusing. And for me, when I was first learning, and even sometimes now, I'll be staring at a big blob of assembly code and I'll just be like, what register was I using? You know, or I'll look at a register and I'll be like, what was that thing even for? So just make yourself a little comment up here to help you understand, and then you'll thank yourself later when you get a little bit too overloaded, or maybe even if you come back to your code a month from now, probably having totally forgotten what you even wrote, then you'll just have a nice little reminder here. It's good to document, and this is one of the ways that I recommend. Okay, so we're saying that R12 and R13 are going to be used. We're loading them up here from the incoming arguments. Now RDI and RSI are free to be destroyed if we want. And of course, we have to destroy them because RDI and RSI were incoming arguments when this function first came in. But now that we're going to be doing a system call, we have to use them for incoming arguments to the syscall. So they're just meant to be constantly destroyed. So we're going to do call code there, and then the standard output is going to be the first argument, and then the string that we did, which is an R12, is going to be the second argument, and then RDX is going to be the next argument, which is R13, which came into us through the second argument. Wait. The string to write came into us through the first argument. The size came into us through the second argument. But if you just kind of look at what we're doing to the system call, it's actually the second and the third. So, I mean, just forget about it. Okay, so we set all that up. Let me make sure I'm not forgetting something by scrolling up real fast. Yeah, so now we can do a system call. One other thing that's very, very important about functions is you have to respect the ABI, and that doesn't just include using the right registers for incoming arguments when you're either receiving a call or sending out a call, but you also have to keep in mind which registers are denoted as callee saved. If something is callee saved, then that means, you know, if I'm inside of print something, I'm being called, that means I'm the callee. So that means if I'm going to use R12 and R13, which are designated as callee saved, maybe I'll pull up that my favorite assembly book after this. But if I'm using registers which are designated as callee saved, then I have to preserve those registers, meaning those registers, they should have their same values from when they first came in on the call when I exit the function. So when I exit the function, those register values should appear to be untouched to the caller. Remember, these registers are not local variables. They're global to the entire system. There's only one R12 on the whole CPU. So every program that runs, every function that gets called, it'll see the same exact R12 register. So if we're not careful about preserving when we have to, we could end up crashing other programs or our own program. So anyway, let's do something that I like to call the Prologue and the Epilogue. That's another nod to my favorite assembly book, which I'll probably show at the end of this video. So Prologue is just, hey, let's preserve the stuff that we need to preserve. We will preserve the R12 with a push, and we will preserve the R13 with another push. We then have to restore them. So right now when we do this push, that just means that whatever value R12 and R13 had is going to go to the stack. So we're going to hit memory. That's not great, but like we have to in this case. We're going to push it onto memory in order to preserve the value, and now we're free to destroy the value if we want. And then right before we return, we'll just pop those values. So that means we're going to go to memory, we're going to go to the stack, we're going to grab the values that we just pushed and put them back onto the registers. Whoops, forgot to do 13 and 12. And I'll call this the epilogue, just meaning like we're done, we're cleaning up. And of course, look very carefully at the fact that the push and the pop sequence are in reverse order. Notice how we push 12 first and we push R13 second. Then at the end, we pop R13 first. So it's backwards. It's like a little shell, you know, the R13s are on the inside and the R12s are on the outside. That logic would persist if we pushed, or if we had to preserve more callee saved registers, if we were using more stuff. The reason we do that is because the stack as a data structure will return data to you backwards in the reverse order that you returned it, or that you sent it into the stack. So if I send a 12 and a 13, let's just say the number 12 and the number 13 into the stack, then if I start popping stuff out of the stack, it's first going to give me the most recent item, which is going to be the 13. So it's going to give me backwards data, and then it'll give me the 12 second. So the type of data structure a stack is first in, last out, or last in, first out, whatever you want to do. Let's see, last in, last out. No, that's a queue. Anyway, so we're preserving the registers. We're doing the system call. We're probably okay to call this function now. So let me see if I can do this. I'm going to comment out all of these things that the say hello function does, and I'm just going to call on print something in order to call that function. But I have to load up my arguments. I have to actually pass arguments. Remember, in the print something function, it's got a signature. It wants a character pointer and a size. We can't just call it without giving it those things, or it's going to look at the registers anyway and just grab whatever junk data happened to be in there. So that would be bad. So first we have to load up the registers. Load up argument registers and call print something. Okay. Load up the argument registers and call print something. So the first thing is going to be RDI, so we have to move something into RDI, and then the second register for the second integer argument is going to be RSI, as far as I recall. If I'm wrong, this is going to go horribly wrong. I'll double check the book after this. And what do we want to do? We want to basically, inside of say hello, we could assume for now that say hello hard codes the pointer and the length. So we'll just say it's going to grab the string from global, and it's going to grab the string length from the global variables. So it's going to load up those two arguments and then call on print something. This still ends up being 3 lines. That's why I was saying before, we're not going to save too much, but we did save, these 2 lines right here, and the system call line. So it's like slightly faster to do. You just load up 2 pointers and then you make a call. I'm not going to talk about loops in this video, so I can't really make the function better, but in the future, when you learn how to loop and learn about null terminated strings, you could basically just pass a pointer to just the string only and then call on a function if the function was smart enough to scan through the string and figure out how long it was based on where the null terminator was. But that's going to happen in another video. Anyway, so if we call print something, it should print the string. Notice also that we're having a function call another function, which is pretty cool. So we have our entry point. It's going to call on say hello, and then once we're inside of say hello, we're just going to load up some arguments and then call on the print something function. The print something function then does most of the work for the printing, and I think we're ready to go. Let's see if this works. All right, so we're going to clear and then just run the program. Oh, that was so fast. That was so fast. I don't even feel like I've proved anything. Let's comment out the system call so that all we really do is just load up some registers and then don't do anything. And then you should see here that the print something function no longer actually does anything. Yeah, because it was too fast. Now, if I uncomment the system call, you know that the print something function is actually doing something, and it's printing the message 5 times. We could also make some more messages if we wanted to, just as a way to make this video slightly more interesting. I'll say MSG1 is going to be a string of bytes, and I'm going to say this is message number 1. Boring, sorry. And we'll do a CRLF there. Actually, you know what? Let's make a function that does a CRLF. Okay, let me just finish message 1 length, and we'll do it equals that special string that you can do in YASM. Am I doing this right? Yeah, okay. So this is message number 1. So now we'll call again with message. We'll call say hello just once, and then we'll call on print something, loading it up first, move something with RDI, and then move something with RSI. RDI is going to take the message 1, is that what I had? Message underscore 1. And then RSI is going to get message underscore 1 length. So basically we're just, print the first message. It's always a good idea to put comments on each line when you're learning so that you don't forget what's happening. In addition to like a comment for the whole block, but I'm not going to do that here. Let's just make sure that this actually works. So it should print 2 different messages now. Okay, so this is message 1. Okay, nice. Let's enhance this a little bit more. Later, I think I'm going to have us print like a, I don't know, a character, or maybe we'll do a return value from something, so we can just show you how to do the return values. But I'm just going to enhance this a little bit more. We're going to say, let's make another function. We'll call it CRLF. The CRLF function, I don't want it to do all the system call stuff because print something already does that for us. I'm instead just going to make another function called CRLF that calls on print message. So now that means I'm going to go CRLF, and that's just going to be a 13 and a 10. Remember, you can define a C string with quotes, but you can also separate quoted strings by commas and also integers just to sort of tack it on. So, you know, this variable right here, it's going to be a sequence of characters representing the string that you see, and then at the very end of the string, it's going to have a CRLF carriage return line feed so that the cursor goes to the next line. So I'm actually going to take that off of message 1 because it's going to be here just on CRLF, and then I'll say CRLF length is going to be 2. I could also do that special thing, probably a little smarter. CRLF. Yeah, I mean, it's better to avoid hard coding things. If you can avoid hard coding the number 2 or any number, just do it. I guess I have to hard code these two though. So CRLF and then length, and so that means in my CRLF function, let's see. Let's do CRLF, immediately return because it's going to be a function. I'll just say void CRLF with no arguments and prints a carriage return new line, also known as CRLF, and so that just kind of describes it. And I don't need to preserve RSI and RDI because those are not callee saved registers, so respecting the ABI kind of helps you in this case. I'm just going to copy paste here, and maybe I'll copy paste that comment real fast too so I don't have to like type that whole thing out. And instead of doing hello string, we'll just say CRLF, and then for here we'll do CRLF length. And now when I call CRLF, it should just make the cursor go, you know, down a little bit. So let's test that out. I took the CRLF off of message 1, so if we actually run this right now unmodified, it should have the cursor, no, what did I just do wrong? On number 28 and 29, instructions expected after label. I guess I forgot to complete something. Oh, I forgot to put, it's a byte sequence right there. And I forgot to put that this is basically a define sequence, you know, the EQU. Okay. My bad. Okay, so now it prints. Notice how the message line, it no longer does a new line and no longer jumps to the next line, CRLF. So that means when the program exits, the terminal prompt is on the same line as the program just printed. That's ugly and awful. So let's call, we could either say, let's call CRLF after printing the first message, or we could just assume that print something is like print a line. I don't know how you feel, but I think if we always called CRLF after every time we printed a message, I would probably be a little irritated. So maybe let's change this to print line and then make it call CRLF. Another thing you could do is, of course, you could just keep adding this like 1013 at the end of every string, but I think I want to try to make this as compact as possible. So let's add the CRLF for now, and then we'll change print something later. So we print the message. Now the prompt should be, you know, a line further down. So great, works. I am now going to take the CRLF off, and I'm going to put it inside of print something, so that right after we do the system call to print the string in question, we'll print a new line. This should now accomplish the same thing that we just saw. Oh no, what did I do? I think I did, I think I have an infinite loop of recursive calls in there somewhere. I had a stack overflow probably. So let's see, what did I just do? Say hello is call print something, and then CRLF is call print something. Oh, whoops. Print something calls CRLF at the end, so I should do one or the other and not have them call both. So maybe just because CRLF is special, maybe I'll just use a direct system call inside of CRLF. I thought I was so clever, but I was wrong. So we're going to repeat a little code for the CRLF, and we're going to load it up with CRLF. Dang, how embarrassing. I like to say this is the most public of my many humiliations. But anyway, so now we don't need to rely on on print something. So this won't be an infinite loop, and it should work if print something calls on CRLF now. Do it again. Okay, it works. So now let's modify print something so that it is just print a line. Print a line. And then that, in my eyes, you don't have to do it this way. It sort of justifies printing a CRLF at the end every single time. So this is just my personal thinking. And then maybe I'll add a comment after prints a CRLF. So now when we call print line, we no longer have to call CRLF. And then when we print that message, should be pretty good. Oh, we got to update that to print line. Then for say hello, let's just double check. We can get rid of this system call code here. Probably a good idea at this point. And then we just say print hello string. And then from the hello string, we can get rid of this CRLF at the end of it. So I'm just going to get rid of that. Actually, let's do it first without getting rid of it. Just so you see, oh, what did I do wrong? Line 61, forgot to update the symbol name. Oh, there we go. So hello needs to call print line because we don't have print something anymore. And try it again. Notice how the first message, hello, my name is, it has 2 line feeds after it because it is calling print line, which will do a CRLF, but then also in the string itself, there's a CRLF. So again, the point is I'm just trying to reduce my typing by leveraging functions to my advantage. Okay, so we got that working now. I'm just gonna print like 5 different kinds of messages. How about 3, so we don't have to sit here and watch me typing for too long. So I'm gonna say message 2, and then I'm gonna do message 3. Message 3, this is message 3, unless I got that wrong. 1, 2, 3, 1, 2, 3, 1, 2, 3. Now we can just call print string on 3 different messages. And I'll just change this to say, print the second message, print the third message, and then I'm going to change that to message 2, and then message 3. All right, so then I'm going to do that again, and then all 3 messages get printed. Nice. So now one more thing, I just want to show you how to return an integer to the caller in a basic YASM x86 assembly function. Again, this will not cover floats. This does not show you how to return floats. With floats, you have to use a different register called XMM0. That's going to be a different video. But for now, I'm going to say all integer or pointer return values, like longs is going to be what we're using, will just be RAX, because that is the register that is designated for return values. So what about this? Instead of just returning the exit success code that I've defined up above, we'll return whatever some function call gives us. Maybe I'll make another function down here, and then I'll say function that just returns a simple long value. And we'll call this function gimme long. It'll take no arguments because we're just keeping this simple for now. And instead of having a void return type, it'll have a long return type because we expect RAX to be loaded up. So then I'm going to say gimme long and immediately do a return because it is a function. And then I'm just going to load up a value from somewhere. Obviously, it's better if you're doing something complicated to stick with registers as much as you can, or defines, and hit memory only if you need to, and try not to hard code immediates into your code if you can possibly avoid it. It's probably a lot better to define a value up at the top in the data area than to just hard code it here, but I'm going to just hard code something here. No, I always second guess myself. I'm going to say exit gimme. I'm going to define something up here. So it's easy to find what value I'm going to return for the gimme. I'm just going to say 88, 89, 90, I don't even know. About 33, I don't even know. So we're defining exit gimme as a symbol to just be a replacement of just the number 33. So down here, I'm going to say, let's have gimme long simply return exit gimme into RAX. Nice, okay. And so that means it's the official return value once you call gimme long. So that means up here, get our, whoops, get out. It's coming from inside the house. Get our return value from gimme long. And again, imagine gimme long might be a big complicated function that decides what a return value is going to be or does something. So I'll start with saying call gimme long. Because gimme long does not take any arguments, I don't have to load up any registers, nor do I have to worry about preserving them or setting them up or doing anything. I just call. But then, let's see, inside of this function, we'll use RAX in order to load up the system call to let it know what function we want from the system call. So we got to give RAX system exit. So that means down here we can't actually use RAX anymore because it's destroyed. Well, now is a job for those other registers. Again, I'm going to use the R12 register. I'm going to do like a little comment here that says register usage. And I'll say R12, maybe I'll do a tab. R12 is going to be hold return value for the syscall to exit, whatever, and that's all we're going to do. So in the prologue, I'm going to push R12. You should probably even preserve registers in the start function because something might, or in your entry point, because something that called you might be counting on those registers. This is going to be probably especially true if you're using GCC to have a main entry point within a hybrid program. So I'm just going to go prologue, push R12, and then pop R12 at the very end. Pop R12. That's not going to work because by the time we get there, it's going to exit the program. I'll do this here. I'll just try to be a good citizen. I'm not actually sure if we need this for a pure assembly function, but it's just a really good habit to get into. And what is it going to cost you? Just a touch memory, just one time right before the program exits. It's not going to be a giant for loop or anything. Okay, so epilogue. Probably I might be showing you bad practice by preserving things in the _start function, but again, you will definitely want to do this for the main when you return from main. So we do prologue R12, epilogue R12. I made a comment there, and then we're going to store the return value in R12. So that means here we're going to move something into R12. It's getting precarious because we restored it right before the system call, but I think it'll be okay. We're going to grab RAX because RAX is supposed to be the return value register. So when we called gimme long, it loaded up RAX with our return value. We then send RAX into R12 so we can use R12. Even though our RAX has been destroyed, we'll still have the return value that we wanted to use. So I'm just going to load R12 up into the first argument of the sysexit call. Let's see if I got this to work or if I totally ruined this. Okay. All right, so let's see here. Why is it not erroring? Gimme 33, exit gimme. Did I load the wrong value? Exit gimme, what is it doing? Exit gimme, it's moving RAX into exit gimme, so you call gimme long, and then you move RAX into R12, and then you pop R12. I wonder if that destroyed it. Let me get rid of this push pop pair because it's supposed to be giving me an error message that the function or that the program did not exit. Maybe this is proof that you don't need to preserve inside of the _start function. Let's see here. Yeah, okay, I guess that proves it. Hey, don't take my word for it. I'm wrong all the time. Prove everything for yourself. Be a scientist, be a computer scientist. Try it out. Try to do something different. Okay, so I guess this is proof we don't really need a prologue and epilogue in just a pure assembly, at least the entry point for start. But if you were calling any other functions, then they definitely need to preserve. And again, if you're using GCC so you can have a main for your entry point, then you still have to preserve. So that means now we are just saying, print the message and then print our other 3 messages. And then the return code is going to be 33. That was the gimme code that we did. So now we know how to return a value from a function. And let me set this back to just 0. So the make system thinks that we succeeded. Run it again. Succeeded. All right, I guess this concludes the video. I hope you had a little bit of fun learning, and I hope you learned a little bit of stuff. And I'll see you in the next video. Hey everybody. Thanks for watching this video again. From the bottom of my heart, I really appreciate it. I do hope you did learn something and have some fun. If you could do me a small little favor, could you please subscribe and follow this channel or these videos or whatever it is you do on the current social media website that you're looking at right now. It would really mean the world to me, and it'll help make more videos and grow this community. So we'll be able to do more videos, longer videos, better videos, or just I'll be able to keep making videos in general. So please do me a kindness and subscribe. Sometimes I'm sleeping in the middle of the night and I just wake up because I know somebody subscribed or followed. It just wakes me up and I get filled with joy. That's exactly what happens every single time. So you could do it as a nice favor to me, or you could troll me if you want to just wake me up in the middle of the night. Just subscribe and then I'll just wake up. I promise that's what will happen. Also, if you look at the middle of the screen right now, you should see a QR code which you can scan in order to go to the website, which I think is also named somewhere at the bottom of this video. And it'll take you to my main website where you can just kind of like see all the videos I published and the services and tutorials and things that I offer and all that good stuff. And if you have a suggestion for clarifications or errata or just future videos that you want to see, please leave a comment. Or if you just want to say, hey, what's up? What's going on? Just send me a comment. Whatever. I also wake up for those in the middle of the night. I wake up in a cold sweat and I'm like, it would really mean the world to me. I would really appreciate it. So again, thank you so much for watching this video, and enjoy the cool music as I fade into the darkness which is coming for us all.